Welcome to the seminar series on cognitive robotics offered by QMUL University of London. My name is Lorenzo Iamone, and I'm extremely delighted today to have Professor David Vernon with us. He's one of the prominent figure in cognitive robotics, and especially I think I would call him maybe the world expert, maybe one of the most expert person on cognitive architectures. And so we are very happy to have him here today. He also had a very interesting, let's say, career path in my view, because he had been taking different challenges in his teaching and research, moving in different places around the world to spread knowledge, which I think is also exciting. And he is also author of a book on artificial systems, which students of the cognitive robotics module at QMUL should know very well, because it's part of their material. And yeah, I'm very happy to have you here, David, and I leave it to you for your talk. Thank you very much.
Okay, so thank you very much, Lorenzo. Thanks for the invitation. It's a pleasure to be here today, virtually, if not physically, but I appreciate the opportunity to talk to you, and I'm going to take you on a tour. In particular, I'm going to take you on a tour of cognitive architectures, and we'll start treating the material in a broad fashion, and we'll progressively deepen it as the talk goes on. So I'll give you an introduction to cognitive science and cognitive robotics, and I'll walk you through a few iconic cognitive architectures, one in a little bit more detail, that's the Isaac one. And then the core of my talk today is the CRAM cognitive architecture, and I'll treat that by talking about its design principles, structure, and operation. And I'll talk about what it can't do as well as what it can do, and that will give me an opportunity to share with you some recent work that's been done in the University of Bielefeld, the situation model framework, and it's going to be the foundation for the next version of CRAM. So cognitive science has a long history. I mean, here I say it starts in 1943 with cybernetics and Wiener's work and McCulloch and Pitt's paper in 1943. But of course, it really has a history going back to James in the previous century. But this was the first attempt really to bring some kind of mathematical formalism to understanding psychology. And cybernetics created the subdomains or paradigms of cognitive science, cognitivism, emergent systems, and inaction. And so this allows me to produce a simple taxonomy of cognition, and we've got cognitivist systems, we've got emergent systems with connectionist and dynamical approaches, and then hybrid as a way of trying to combine the best of both. And students of artificial intelligence will recognize this taxonomy because this is exactly the path that's been taken by AI since 1956. The differences between the cognitivist and the emergent approaches are fairly significant and not as trivial as some people explain them to be. So for example, with the cognitivist approaches in cognitive science, it's all about syntactic manipulation of symbols, whereas in the emergent, it's more about self-organization. In the cognitivist paradigm, the epistemology or knowledge is agent independent. It exists in the world and everyone has access to it. But in the emergent paradigm, your knowledge is agent dependent. It depends on you as a perceiver and as a cognitive agent in the world. It tied in with that in the cognitive side, embodiment doesn't play a role. The cognitive model works on any platform that can support its operations, but that's not true in the emergent side, again, because your body is part of your cognitive model. When you adapt in the cognitivist paradigm, you learn new knowledge, but in the emergent paradigm, you learn new dynamics. And that allows me to distinguish between what cognition is in both paradigms of cognitive science. It's about rational goal achievement in the cognitivist tradition, and it's more about self-development and self-maintenance and autonomy in the emergent side. Now, why? And then hybrid tries to bring both of these together and get the best of both worlds. But I want you to be aware that there's a different way of interpreting that hybrid. There's a big H hybrid and a little h hybrid. The big H hybrid is an effort to try and reconcile all the differences between the cognitivist and the emergent. And that's a difficult task, given that there are fundamentally opposing positions and stances and indeed philosophies being taken. So when people talk about hybrid systems, they're, for the most part, they're talking about little h hybrid, and that means that they're talking about systems which have symbolic processing and sub-symbolic processing, typically with some form of connectionist system. So just bear that in mind. It's little h hybrid typically we're talking about when we talk about hybrid systems. So if we have these different paradigms of cognitive science, then cognitive architecture was a term which was invented by Alan Newell, 1987, for his book in 1990. So the term cognitive architecture has its origins in the cognitivist tradition, and that it was subsequently borrowed and used in the other traditions. And that's important because a cognitive architecture, then the cognitivist tradition, has a very, very specific meaning. And I'll tell you about that in just a moment. So let's talk about cognitive robotics. So how does a cognitive robot work? Well, it perceives, it learns, it anticipates. What does it anticipate? It anticipates the need to act, and it also anticipates the outcome of any action that it can take. And this allows it to choose the actions which are most appropriate in the current context. And then it acts in the world, and it adapts based on its actions in the world, and it improves its performance as time goes by. But the key feature of cognition in cognitive robotics is this capacity to anticipate the outcome of events and the need to act prior to acting, and that's significantly important. But something's got to bring all this together. So something is to orchestrate all of these processes, and that something is called a cognitive architecture. And as I said, in the cognitivist tradition, that's where the term cognitive architecture arose with Alan Newell. And Alan Newell introduced this concept of a unified theory of cognition, which is effectively a model of cognition which covers everything. All of the capacities and capabilities in the cognitive system from all the different disciplines that are interested in it. This is a page of his the early proofreading copy of his of that book, and this is where the term cognitive architecture first appears. And in the cognitivist tradition, then a cognitive architecture effectively is this aspect of the model that's relatively constant over time and relatively independent of the task. So it's not domain specific and it's not task specific. So to complete the model, then what you do, you add knowledge. So you have your cognitive architecture on the one hand, your framework, you have your knowledge, and that together then provides you with your model of cognition, your unified theory of cognition, as it were, from Alan Newell's perspective. The emergent side and paradigm takes a completely different spin on things. It's much more focused on development. So you initially have a capacity for cognition, but not the capability, and over time that capacity develops into a full cognitive state. And then there are different aspects to development. We've got here Jean Piaget, who adopted principally the perspective that it's development by exploration in the world, and then Lev Vygotsky, who took a more social perspective that development is impacted by the interaction you have with the world, with other cognitive agents. And these are complementary. You need both if you want to develop a cognitive system in this paradigm. So the focus here is less on knowledge and much more on skill, and in particular on anticipatory adaptive skill construction, and also on the morphology of the physical body. And this is important. And I'll just kind of a sidebar here. When people say something is embodied and they say because it's got a body, like a robot has a body, that does not mean that it is embodied. To be embodied means that that body plays a causal role in the cognitive model. It's not just merely a mechanism for acquiring sense data and then forcibly interacting with the world. That having a body is not sufficient to be embodied. Embodied implies also that that body plays a causal role in your cognitive model. And then just as we had hybrid systems with the paradigms of cognitive science, so too we have hybrid cognitive architectures. But here I'm just alerting you again that it's little h rather than big H hybrid. And all cognitive architectures of both the cognitivist and the emergent paradigms, they must all identify what modules are in the architecture, the relations between those modules, and specifically, and this is very important, it's often left out, the algorithmic and the representational details. Without these, you do not have a cognitive architecture, you simply have a boxology. So you need to commit to algorithmic and representational details. And this is something that's been emphasized for the past 14 years by Ron Sun. There are many desirable characteristics of a cognitive architecture. Ron Sun has a very famous paper called Desiderata for cognitive architectures. Pat Langley has a paper on this. Jeff Kritschmar addressed the developmental aspect. And it's a great paper, the Ron Sun one, so we thought we'd get in on the act. Klaas van Hosten, a developmental psychologist, and Luciana Fadiga, a neuroscientist, and I wrote a short paper which identified 10 desiderata for a cognitive architecture if it was to be capable of development. So this then summarizes the situation with cognitive architectures. We've got an organizational decomposition that's shared by them all. On the left-hand side, the cognitivist cognitive architectures focus on knowledge, and on the right-hand side, it's effectively more about the phylogeny, the state of the system before it starts developing. So the basis for development. And there are many different cognitive abilities that you'd like in your cognitive architecture to facilitate. These 7 were identified by a landmark survey of cognitive architectures in print this year, in 2020, by Katsurub and John Tsatsis. They didn't include prospection, which I always include because I think it's extremely important, mainly because it was drilled into me by Klaas van Hosten, the developmental psychologist, that it is crucially important to cognition. So if you want to look at different surveys, there's several of them out there. The Katsurub and Tsatsis one is absolutely, it's definitive. But the one thing they don't do is that they don't provide a summary of each individual cognitive architecture. Rather, they audit them to say what capabilities and capacities they have. If you want to read a summary of each of the cognitive architectures, there's a summary in the book that I've identified here. I also point out that the term cognitivist is a valid word, and it's been around for decades. But as a reviewer of my book said, please don't use it, it's an ugly word. But I didn't make it up. But Katsurub and Tsatsis prefer to use the term symbolic. So you'll hear people talk about symbolic architectures when they also mean that they are from the cognitivist tradition. So here's a graphic from the Katsurub and Tsatsis paper, just pointing out that they have symbolic versus emergent and hybrid. So they do adopt exactly this taxonomy, just switching symbolic, a nicer term than cognitivist. So SOAR is an archetypal cognitive architecture. It's actually the one that was developed by Newell and John Laird and Paul Rosenblum. I'm not going to walk you through it. I want to show you this picture. This is the picture of SOAR today, which is nothing like the picture of the cognitive architecture back in 1986 or 1990. And it has evolved over the years. And at the end of this talk, I'm going to give you a link to a website where you can see the various people, and I'm going to take you on a tour through now with these cognitive architectures, John Laird being one of them, and they're going to give, it's a place where you can find videos, 15-minute videos where they give an overview of their cognitive architectures. ACT-R is another famous iconic cognitive architecture. This is John Anderson's one. It's also a unified theory of cognition, just like SOAR. And it focuses more on mapping functionality to different regions in the human brain. Clarion is another famous cognitive architecture. This is Ron Sun's famous architecture. The reason that this is special, and it's a very special cognitive architecture, is that it was one of the first to take very seriously this idea of having both symbolic and sub-symbolic processes, and not as distinct ones, but they are distinct, but they share information between these two subsystems. So there's a flow of information between sub-symbolic and symbolic in both directions. And it's one of the few cognitive architectures which attempted to take that seriously. And the emergent side, there aren't so many of them. Jeff Kritschmar's brain-based devices one is worth reading. And again, there's a video by Jeff that I'll show you at the end of this talk if you want to spend 15 minutes reading and listening to him tell you about this approach to emergent cognitive architectures. Think of the brain-based devices as not a connectionist system, like a neural network, deep or otherwise, but more like modeling the nervous system as a whole, and the interaction between the different parts of the brain. So it's more populations of neurons rather than a feed-forward or a recurrent neural network. And then Isaac, I want to spend a little bit of time on this one. This is a cognitive architecture which was developed by Kaz Kawamura in Vanderbilt University. And again, Kaz has given us a nice 15-minute overview of his approach to cognitive architectures. And it's, I use this, this is my favorite cognitive architecture for when I'm teaching, because it's got pretty much everything that you would typically expect to see in a cognitive architecture. So I want to spend a little bit of time going through it, and because it'll help me explain something later on at the end of the talk when I come to the situation model framework. So think of this as a little bit of an investment for the latter part of the talk. So Isaac is a hybrid cognitive architecture, and each element of it is effectively a software agent operating asynchronously and communicating with each other by message passing. And for those of you who are familiar with Ross and YARP and component-based software engineering, this predates this. So he anticipated all of these developments in cognitive robotics. So each agent we've got carries out has a certain responsibility. So perception agents, we've got agents then for different actions. And it's got this first order response agent, which is significant because it means that you can have a very fast response to something happening in the world if that's necessary. There are three memory systems. There's short-term memory, long-term memory, and working memory. And in cognitive architectures, most modern cognitive architectures have all three forms of memory. And it turns out that the working memory system is much more sophisticated than most people think it is. It is not just cache memory, as I'll point out later on in this talk. It's much more sophisticated than that. And indeed, there's many different versions of it. I was reading a paper yesterday which identified 9 different definitions of working memory. So don't get the impression that working memory is a trivial cache of information from short-term and long-term memory. It's not. So short-term memory is the memory which effectively allows you to represent what's happening in the world. Isaac has a sensory ecosphere, which is a way of encapsulating from several modalities everything that's happening around the robot. And it also has an attention system, which is very, very important in cognitive architectures. Long-term memory comes in 3 different flavors. Again, this is key for cognitive architecture. We've got semantic, episodic, and procedural. Semantic, facts about the world; episodic, autobiographical information; and then procedural, your skills, effectively. So your episodic memory turns out to be extremely important. It's effectively what your experience as an agent, as you experience the world, and you use these experiences in order to predict the future so that you can act effectively in the world. So it comprises many different things like your emotions, the outcomes of your actions, the actions, and also some valuation of those actions, whether they were good or bad, or whether you'd like to see that happen again. And they are linked together in Isaac, forming a network of them, and it's a multi-layered network. The working memory system in Isaac temporarily stores information coming from the short-term memory and the long-term memory. And these, in this particular case, Isaac has a type of short-term cache memory, but it's actually modeled on one of the original models of working memory by Baddeley back in 1986 and 1974 originally. So it's built on a sophisticated model of working memory from cognitive science. You've got the self-agent then on the right-hand side, and this is effectively doing the deliberation in your cognitive system. So while your first-order response agent allows you to do habitual work, so based on things that you know, the self-agent then can do some reasoning if the solution to your current problem isn't apparent. So there is the central executive agent, CEA, and an internal rehearsal system This is really important, this internal rehearsal system. You'll see it in almost every cognitive architecture, very often referred to as the internal simulation system. And then you've got your goals and motivation subsystem, which determines what the cognitive architecture actually does. So the intention agent and the affect agent together are responsible for driving the behavior of your cognitive system. And the internal rehearsal system is used, as I'll show you in a moment, as a way of determining whether the actions that you've selected will give you the outcome that you want. So this is the way that Isaac works. So first of all, the first order response agent responds to sensory triggers. And it is also then responsible for carrying out tasks. So if it gets a task from its user, it goes to its procedural memory, it sees if it finds a chunk that matches the current context, and it transfers that to working memory along with the current percepts. And then this is then handed over to the activator agents, which then execute. And it will suspend execution if a reactive response is required. So this circuit here always takes priority, which makes sense. If something is dangerous, if something is urgent, you want to suspend what you're currently doing and react to it. If, on the other hand, there isn't a skill in the procedural memory which matches the current context, then the central executive takes over. And it goes to your episodic memory. Remember, that's your memory of your past experiences. And it sees, well, was there something I recall that is similar to this context? And then it transfers that into its internal rehearsal system. It uses that episodic memory to see, well, if I was to do this again in this current context, what would be the outcome, and is that what I want? And if it is, then it selects it, transfers it to working memory, and then on to the activation agents for execution. So that's our broad, shallow overview of cognitive science, cognitive architectures, and a few iconic cognitive architectures that you'll see if you study the area, with a little bit more detail in Isaac, because it helps to understand how these different components of a cognitive architecture work together with that little walkthrough. Now, by way of contrast, I'm going to take you through in more detail. I'm going to give you an overview of the CRAM cognitive architecture. So this is another hybrid cognitive architecture. It was introduced and developed by Michael Bates for the last 11 years and beyond that. I mean, Michael has been developing this for many years. And it's been developed very substantially over the last 10, 11 years. And my goal today is to show you where it's going to be going in the next 4 years and beyond. And it was designed specifically as a robot cognitive architecture in order to focus on robot manipulation in everyday activities. So let me just give you a little clip from a video, give you some respite from my voice. Okay, so you can watch the video in your own time, but this is effectively what CRAM enables that PR2 robot to do. So CRAM was controlling that PR2 as it was laying the table and then clearing up afterwards. So the whole point about CRAM is that it is designed to be able to interpret instructions or action requests which are underdetermined, like fetch the spoon, from where, and put it on the table, where on the table. So none of these things are specified. And so we talk about implicit to explicit manipulation. So you've got a vaguely stated high-level goal, and somehow CRAM has to map that onto low-level motions which will accomplish the goal successfully. And that mapping is accomplished using a technique you called a generative model. Think of it here as effectively a combination of symbolic and sub-symbolic knowledge representations, which can determine the motions that are most likely to result in successful action. There's a more technical definition of it, which I'll talk about a little bit later on. But just remember the term, a generative model. So how do you do this mapping? So the goal is requested by the agent, or indeed by the robot itself, if it's operating autonomously. And it then tries to identify the parameters of the motions. So we map from what's called a generalized action plan, and that's the key concept in CRAM, and we map to a motion plan. And this happens in a three-step refinement process, which I'll walk you through in just a moment. But the process is called contextualization. So contextualization is this transformation from general to specific motion plan for that particular task, using the generative model. And in CRAM, we have different ways of talking about this transformation. We talk about performing an underdetermined action description, like fetch the spoon, or executing the generalized action plan. That's the computational representation of that description. And then within that plan, there are these things called designators. In particular, there's a high-level action designator, and this effectively is a placeholder for as yet to be determined information as you're executing that plan. So I'll explain that. Now, a key issue here in CRAM is that it's adopted an approach developed by Randall Flanagan, where you break your motion plan up into phases. In CRAM, we have a slightly more fine-grained approach to it, like reaching, grasping, gripping, lifting, going, reaching again. Now, the key thing here to notice is that there are motion parameters associated with each of these primitives. And that's the job of your cognitive architecture, is to find what are the poses of your gripper in order to do things. What kind of force should you use? How should you approach it? So what we need to carry out a robot program in cognitive robotics is we need to know the values of these parameters. And that, in essence, is all there is to cognitive robotics. But the problem is it's underdetermined, and you need knowledge from the perspective of CRAM in order to determine what these parameter values are. But that's the key thing to understand. What we're after here are the parameters of these motion, the values of these motion parameters, which when provided to the action executor will allow the action to be carried out successfully. So a quick overview then of the structure of CRAM. It's got 5 different components, and I'll walk you through them. So first of all, it's got the CRAM Plan Language Executive, we'll just call it the Plan Executive for short. And its job is to interpret these generalized action plans. I'll show you an example of this in a second. It's written in Lisp, as are the plans. So here's an example of a fetch and place plan written in Lisp. You can see here in red, I've put in the action designators. So we've got an action for fetching, we've got an action for placing. So this is a fetch and place generalized action plan. And the point is that as you expand that, then you have effectively what you want to fetch. You want to fetch an object of what type cup. You want to then fetch it from where. So this is a location designator. The object designator tells you what type of object you want to manipulate. The location says where you should go to get it. And then we have another object designator which says where you want to put it. So the plan executive then resolves these designators that I've just shown you here, because these are just placeholders. It doesn't know them when the plan has been written. And at runtime, then it resolves them, and it resolves them by referring to your perception system, and also in particular by referring to the NOROB knowledge representation and reasoning system. So this over here, as we'll see in ROMOB, is what is going to determine the values of the motion parameters that I mentioned earlier on. So that's what we're after. We're after what values will make these motions successful for carrying out this action. So NOROB2 then is the knowledge representation and reasoning executive. It uses this concept of a generative model to identify these motion parameter values. And think of the generative model in a more technical way as being it's a joint probability distribution over the key things that matter in robotics. The motion parameter values, that is to say, if I was to do this type of motion, I would get this type of outcome. And so you get this mapping between your action and your effect, and that's what your generative model is effectively modeling. And what you need to do is you need to sample that to find the parameter values which give you the outcome that you're looking for. So this is the idea. It maps from an actions to the motion parameter values that will succeed in accomplishing that action. There's a lot in NoRob. There's an ontology and a set of axiomatizations. The ontology is all of the knowledge that the robot has, and the axiomatizations, the axioms, effectively then tell you what roles these objects can play. For example, a mug can hold a drink. It's a receptacle, and you can pour things from it. There's a generalized symbolic knowledge base, which is a way of encapsulating in a general way knowledge based on experience from what are called nemes. Well, what's a neme? A neme is, in CRAM speak, is a narrative-enabled episodic memory. Now, you already know what an episodic memory is. It's autobiographical memory. But in CRAM, there is a narrative which goes with it, which is, so it's not just a recording of the robot's experiences, all its percepts, poses, and control signals as it performs a task, but also a symbolic language-based narration describing what that task is doing. So you have here your sensory motor data from your low-level sub-symbolic, and then your symbolic representation of what that narrative, of what that episode is it's trying to accomplish. So your neme is a sub-symbolic and symbolic hybrid representation. So think experience plus narrative explaining what it's all about. So in that case, our episodic memory in CRAM includes not just purely autobiographic information, but also procedural knowledge as well. So it's more than just declarative knowledge. And it allows the robot to answer lots of different types of queries, which would be useful when it's reasoning about the task it's performing. Very importantly then, CRAM has an inner world knowledge base. Now this is implemented using a geometric reasoning system and a very high quality virtual reality system with a physics engine. And this is part of the video that you saw earlier, and it effectively allows CRAM to simulate the execution of an action before it does it in the real world to make sure that it is going to achieve the outcome that it wants. So you simulate the outcome of your candidate actions, and that establishes the feasibility of the action. And effectively, so you do this prior to committing to doing it in the real world. It also provides symbolic names and properties for each entity, so you can infer background knowledge, like, for example, where an object is stored. So that milk is perishable, and you would look in a fridge to find it. So this internal knowledge base has these two roles. It's a way of reasoning about the outcome of a possible action, but it also is a way of representing a belief about the state of the world, that the milk is in the fridge, for example, or the spoon is in the drawer. So these two different types of knowledge is what's encapsulated in this part of NoRob. It's also a learning mechanism because you can be doing these simulations offline, and that gives rise to experiences, and they can then be stored in your NEMS episodic memory base. And the last one then is the virtual knowledge base. And this is a very, very elegant technique. It allows symbolic information, sub-symbolic information from, say, perception and the motor system to be represented in a symbolic fashion, and therefore it can be reasoned about. And it also provides a way for the plan to be able to reason about itself. All of this then is wrapped up in a logic-based language interface, which allows NoRob to be treated as a purely symbolic knowledge base. And then the plan executive can query it. So you get this idea, a query from the plan executive during the task execution. So the plan executive needs to know what the parameter values, so it asks NoRob. And so you get this kind of, Michael Bates refers to it as a kind of a Siri for robots, which is a nice way of encapsulating it. It also facilitates metacognition, which I'll not say a lot about today. We've got an action executive, which carries out the plan once the parameter values have been identified, and a perception executive, which is very important for identifying the current state of the world, called Robo Sherlock. Metacognition is implemented in the subsystem called Cogito. It's effectively a way of improving the way that CRAM does things, sometimes called meta-reasoning. But the idea is that you can improve your cognitive capability. You can develop over time using a technique called PEMS. PEMS are a way of saying, okay, I know how the world works, and I can identify a subset of that high dimensional space of possibilities, and I'll only work within that. And it makes what would otherwise be an intractable task tractable. So let me walk you through briefly how all of this works. So we're going to map from a generalized action plan to a motion plan. We need our, over here, we need our parameter values. And so the robot has a generalized action plan. So fetch the spoon and place it on the table. This is my generalized action plan. We've seen this before. And the 3 steps in the contextualization then are create the plan, expand it by identifying all of the action designators that we need here, and all of the object designators and all of the motion designators, which are required in order to build this low-level plan that we saw earlier. This then is passed as a query to NOROB. NOROB and said, can you please provide me with the values of these designators? NOROB does that using its generative model and using its internal simulation to check, will it work? Passes back the values to the plan executive, which then passes it over to discard the action executive, and your action gets executed successfully in most cases. Our concept of a cognitive architecture in CRAM has another useful meaning. It's viewed as an interface effectively to low-level computational representations and processes. So metacognition is the idea that your plan executive can expand, so it can self-program. It can. This is the idea of expanding the space of possible actions. And so if from the perspective of CRAM, what you're doing then is effectively you are extending your generalized planned language and therefore extending your interpreter. And that's what metacognition does in CRAM. So when it does this, when it updates the knowledge base as it expands and enlarges effectively the language of the generalized action plans. As an interface, though, CRAM then allows many different types of robots to be used. So it's robot agnostic, and it hides all of the implementation details. So this is why it's useful to think of a cognitive architecture in this particular instance as a form of interface between your robots and the high-level tasks and then their underlying computational processes. So that's what it can do today, and where are we going to go in the future? So in the last 10 minutes, I'll tell you a little bit about what it cannot do and how we're going to try and change that over the coming years. In particular, what we want to have much more flexible, context-sensitive plans. And so we want to move from a state today where we can perform known actions with known outcomes, just the way that I showed you. We've got a generalized action plan. NOROB knows all it needs to know in order to identify the motion plan parameter values in order to accomplish that task. But that's not enough for true cognition. True cognition exhibits a versatility that is hard to achieve. And you can characterize that by saying what we would like to be able to do is we'd like to be able to use known actions to accomplish new outcomes, to be able to use new actions to accomplish known outcomes, so do things in new ways, and then to be able to do new things with new actions. So giving you an example of that, so over here, in this quadrant, the idea would be that if you wanted to reach for the milk in the fridge, but something was occluding it or hiding it or obstructing it, then you wouldn't need a new action. You'd need to move it out of the way first. That other thing, if it was a bowl, in order to be able to grab the milk. Let's say you want to do something new. You want to put paste on a pizza base. Well, we've got a pick and place action plan. Well, I can use that to get a new outcome by spooning from the jar to the pizza many different times. So I'm accomplishing a new outcome with a known action. But then, most interestingly of all, I'd like to be able to do something different. I would like to be able to use a brand new action like smearing or spreading, so that you would only do one pick and place and then adopt a new action to do this new thing of covering your pizza. So this is where the future of CRAM lies. And we can do parts of it today. These are all the different things you would need in order to be able to accomplish these different forms of new outcome and new actions. And so that's where we'll be going over the next few years with CRAM. So how are we going to get there? So in the last few minutes, I'll tell you a little bit about some recent work, which was done as part of a research group in the University of Bielefeld with research fellows from all over the world, working on a thing called the situation model framework. So it ran for from October 2019 to July 2020, and there will be a closing conference sometime soon. The pandemic disrupted our plans a little bit here. So there's a lovely position paper, which was written by Werner Schneider, Josephine Albert, and Helga Ritter. And it is a wonderful encapsulation of this approach, the situation model framework. And what I want to do now is take you on a quick whistle-stop tour of this. So there are three foundational things. First of all, it's all about action. And let me just say that again, because it's so important. Cognition is all about action. So don't think cognition is about thinking. It's not. Cognition is about effective action, acting effectively in the world. And that you can also have different behaviors when you act in the world, and you can scaffold them. You can have simple behaviors and you scaffold them together and have more complex ones. And there's a lot going on in the world, so you need, and there's a lot going on in your cognitive system, so you need an internal attention system, which allows you to prioritize things. So these are the piles, the foundations for the situation model framework. And on top of that, then the capstone, if we will, you have this representational idea called a behavioral episode. Now, this is important because it is an unusual representation because it combines actions and perceptions into one unentity. So it's a joint perception action representation. And it's an abstract one, so it's not encumbered with very, very low level motor details. And it's a way of capturing effectively the outcome for a given scene. If I was to take this action, what would be the outcome? This should remind you a little bit of our generative model that I mentioned earlier. So these behavioral episodes then allow you to model the behavior of an agent working in the world. And so there are three different aspects to the framework. There's the two-system approach, which sometimes called the dual process approach, and sometimes called the system one, system two, after Kahneman's work. I think it goes back to, but it goes back earlier than that in the 1980s. And the idea here is that well, I'll tell you about that in a second, so let's just move on. Working memory, I warned you that that was going to be important. Now, working memory has a limited capacity, and it also has an attentional aspect to it. And then finally, there's this idea called a cognitive map. Now, contrary to what most people think a cognitive map is, it is, of course, associated with navigation in the world and effectively a map of where things are. But it was invented, the term was invented by Tolman back in 1948, and he meant it in a more general way. I read the paper yesterday because I wasn't aware of this. But it turns out that the original meaning was as an abstract map of causal relationships in the world. So it's a network of the causal links between actions and percepts in the world, if you will. So it's a very general idea. So the two-system approach, we've got habitual, as we had remembered. This is why I told you about CRAM, not CRAM, about Isaac, the idea of the first order response. So the habitual is system one. And then deliberation, that's like the central executive agent. So the idea where you cannot just do it by availing what you currently know, you have to do some reasoning. So system one will retrieve behavioral episodes, candidate ones. It'll have a competition, it'll choose one, and then it'll execute it, just like the first order response agent does, for example, in Isaac. But system two then has a working memory. So it allows you, and this is the key thing here, to construct new novel episodes. So therefore you can invent new sensory motor contingencies, another way of experimenting in your head with different actions and different outcomes, and then simulating them. And then if they work, you assimilate them into long-term memory, but you could also refine them. So that's what system two is doing. And that's where you get your flexibility. So system 1 is like reactive control of action, and system 2 is more like prospective control of action. So that's the situation model. And they both have access to long-term memory, as I said. So, okay, and so your context sensitivity is achieved through your attentional processes. And your internal simulation then allows you to adapt according to your metacognition. So that's the other element of the situation model framework. And then finally, the cognitive map, which was coined by Tolman in '48, is a very, very rich, it's richer than the cognitive map that for example, that you would associate with the hippocampus and place cells and grid cells. So it's a more higher, it is that, of course, but it's more than that. It also allows you to build abstract maps of an abstract map of causal relationships in the world. So that completes the situation model framework. And so this captures in my little cartoon here the idea that it's a way of constructing and simulating and enacting and refining behavioral episodes as you're trying to figure out how to accomplish a particular task using this joint perception action representation called a behavioral episode. So it's crucial that you understand that working memory is both process and representation. It's not just a way of storing information, because it's got this way of reworking your behavioral episodes. And then you mentally execute these before you do anything. So that's what the Probehandeln is the German term. It's a trial execution. That's the German word for this. So this is where CRAM 2 is going to get its power. It's going to try and bring this together. And of course, we need to commit to formalisms and representations and processes to bring the situation model framework about. So that completes my overview. I know I went very, very quickly. Of course, you've got the video here of this to look back at, but if you want, there's also more material. So I took most of the material for this from an open course, which is available online, cognitiverobotics.net, and it's effectively module 7. So in I've covered 4 lectures in the last 45 minutes. And finally, as a treat, there was a workshop which we held just 2 weeks ago on cognitive architectures. And we had an amazing array of speakers from around the world. People like, there's Casco Amura, that's Isaac, John Laird with SOAR, Helga Ritter. These are all 15-minute videos, so low overhead, but they're really, really packed full of information. Helga Ritter will tell you here more about the situation model framework. If you're interested more in the social aspect of it, Agnieszka and Alessandro will have more on that. Angelo has information or more on the language side of things. Tannen, it's just packed full of interesting information. There's Jeff Kritschmar. This is the BBD, the only emergent one that I mentioned in this talk. And of course, Yanis Demiris with his wonderful hammer architecture, and Sean about the leader one. So, and Tommy Poggio in MIT has some amazing things to say about how to solve the cognition problem. I mean, it's just incredible. And well, Yanis Alamoin is focusing on action, Minoru Asada on, well, enough. Okay, have a look at them. They're great videos and you'll learn so much from them. I certainly did. So that's it. I'll finish there. I thank you very much for your attention. I hope you enjoyed it. And you've managed to get through all of my 162 slides in just about the time available. If you've got questions, I'll be delighted to try and answer them.
Wow, fantastic. Thank you very much, David, for bringing us on this journey. It was very good. I think so. Everybody's welcome to write questions in the chat if they want, or to pose their question live. I think there is already a question there. Maybe I can just read it. To what extent do you think large cognitive architectures offer insights into human cognition, as opposed to just taking inspiration from human cognition? It must be challenging to compare the high-level behavior enabled by these large frameworks to behaviors of participants, for example, in a psychological study.
Yeah. So that's a great question, and thank you for asking it, because it allows me to say something that I didn't focus on here. Here, in this talk, I've been talking about robot cognitive architectures. I've been talking about building a cognitive architecture, designing and implementing a cognitive architecture so that we can get robots to behave cognitively and to do the type of things we want our cognitive robots to do. That's not the reason that cognitive architectures were invented as a concept. Alan Newell's original idea was to create a model of human cognition. And so his unified theory of cognition, which I mentioned, is a model of human cognition, just as ACT-R is, just as SOAR and LIDA. These are all, and Clarion, these are all, in effect, cognitive science models of human cognition. And they are there as adopting this analysis by synthesis approach to science, so that to understand something, you need to build it. I mean, it mirrors Feynman's phrase that what I cannot create, I do not understand. It's a famous message he wrote to himself on his blackboard in Caltech. And so that's what a cognitive architecture was originally invented for. And it's, if you listen to these talks here, this is the LIDA one. This is all about human cognition. Jeff Kritschmar's is about human cognition, also about robotics, other cognitive architecture. SOAR is exactly a model of human cognition. So that's what they're there for. And it's analysis by synthesis. You try and create it to give you insights, to test your hypotheses about human cognition. So that's what these unified theory of cognition architectures that I gave you a brief overview of at the beginning are all about. Which contrasts with, for example, ARMR, which is a robot from Tama Mafsra's group, ARMRX. That's about building a robot cognitive architecture. Same with DIARC from Matthias Schutz, and CRAM, obviously, from Michael Bates. Have I answered your question?
Well, maybe I can ask a follow-up then,
yeah.
While maybe Tom can also write something more if he wants. But I think there was, let's say, also a second part of the question, which was how can we, let's say, compare that, for example, to human studies? Because sometimes we have examples in which we can directly compare results from, let's say, cognitive robotics to specific studies in psychology. And of course, what happens with those studies is that they're restricted to one single task, right? To one single thing. So it might be difficult to compare an architecture, like, or the results from an entire architecture to what we see in humans. Do you have some insight about that?
Yeah, but in fact, this is the idea. So what you would do is you would hypothesize a particular model. You would then get your cognitive architecture to enact that in real time, and it should behave as humans do. And so John Laird and Stan Franklin, who was the architect of LIDA, they carry these experiments out. And I know in at least one case, I can't remember, it was in one of these videos, they talked about where by using the cognitive architecture, they were able to predict a result, which they then validated and verified empirically with psychological experiments. So this was the other side of it. It's not just that the cognitive architectures can be inspired by and replicate human cognition, but they should all, if it's a good model, it should also have a predictive capacity, so that it should be able to predict how humans would behave in certain instances. And I think it was in this video that I saw Sean talking about how LIDA did that, or somewhere else. I'll try and remember where it was. Have I answered your question now? So.
Sorry, I had a little bit technical problem. Okay, so I think there is a related question, or let's say another question on the chat, which is about whether the main focus in terms of research and development on cognitive architecture is to create a generalizable architecture that could work in many different contexts, or the best architecture for a specific set of tasks.
The goal, okay, again, let me be clear here. I mean, there's these two classes of cognitive architectures: robot cognitive architectures, which I've been focusing on today, and then cognitive architectures writ large, the unified theory of cognition ones, which are aiming for exactly this versatility. So they're a part of this thrust now of reclaiming the original goal of AI, which was the versatility of human intelligence, rather than the amazing. I mean, AI over the last 10 years has changed fundamentally with the deep learning revolution, but it's narrowed its focus, and deep networks are extraordinarily powerful, but they're not versatile. Whereas a cognitive architecture is reclaiming this original idea, the original idea from 1956 of AI as replicating the versatility of human behavior, the adaptiveness, the ability to do one-shot learning, to be flexible. And that's what I've been talking about today. So we would like that in our robot cognitive architectures, and for our unified theory of cognition architectures like ACT-R and SOAR, that's exactly what they're aiming for. So they're part of this artificial general intelligence paradigm that we have today, this reclaiming of the original goal of AI. Because AI was part of cognitive science to begin with. It was its sister, and it was when it was launched in 1956. Have I answered your question there? This isn't actually what I came to talk about today, but it's very interesting because it's the bigger context of cognitive systems, which is really important.
Yeah, thank you for this. So there is another question in the chat. You mentioned systems 1 and 2 in thinking fast and slow.
Yeah.
The authors point out inappropriate usage of those systems that leads to some problem in decision making. Is it something that is being seen or might be seen in cognitive architecture? Do you think it might help us find strategies to sidestep these problems?
There's a big problem that you face in what modulates the switching between the two processes. So that when does system 2 take over? I mean, and also when can you delegate to system 1 what system 2 had been responsible for? And so there are various approaches to the way people try and realize that, but it's not a solved problem at all. So they call it dual process theory, or I think it was Norman Shallis invented this. Kahneman, of course, is very famous for the thinking fast, thinking slow, and the system 1, system 2 approach. But it's all about the distinction between habitual behaviors and deliberative behaviors, and how you switch between the two and how you modulate. And it's not a solved problem. And that's what we are trying to model. That's what we will be trying to model over the coming years in Bremen, on the basis of the situation model framework.
Okay, I have, well, I will have tons of questions, but I will ask just a couple maybe until there are others on the chat. So one thing that you pointed out somewhere in your presentation, maybe not in an explicit way, is that this cognitive architecture, especially those for robots, they are cognitive architecture, but at the same time, it's also software architecture. And it's also control architecture.
Yes.
So I was wondering, like, in your view, how much the fact that it has to be also software architecture and it has also to be a control architecture influences the cognitive description of it.
Yeah, thanks for that. I took out the slide on that because believe it or not, I did take slides out before I gave this today. I had 220 this morning. I got it down to 160. So that was one of the ones I took out, and I now regret it, because this is something that I'm passionate about. The cognitive architecture is not just a conceptual framework. It's a realization. And I emphasize that you have to commit to formalisms, and you have to commit to the specific processes and the specific representations. And this is a point that's made very, very forcefully by Tamim Astor in his talk here. And he talks about the fact that it must be both controller and a software framework, as well as this orchestration, if you will. So it's got to be both. I mean, if your cognitive architecture can't be realized in a software framework, it's useless. Right? It's a paper architecture, and that's not going to assist you in your analysis by synthesis because you haven't synthesized anything. You've got to run your experiments and see what behaviors you get. And I won't say there's a tension between this because I don't see it that way. I think that you just have to be cognizant of the fact that you have to go all the way down the stack, from your computational theory all the way down to your implementation. And you then need to choose a particular software engineering paradigm that suits the realization of your architecture. We saw with Isaac now here, I'm very glad I showed it to you, that it was an agent-based architecture. So it adopted effectively the component-based software engineering approach, which is the flavor of software engineering that most of the robotics community have adopted, using, say, ROS, for example, the publish and subscribe paradigm, or YARP, or whatever else you want to do. Tamim's got his own version in ArmorX, but he's got bridges to ROS and bridges to YARP. But it's both software framework and cognitive model. It's both, and in between the formalisms, the mathematical modeling of the processes, and the representational details, the way you represent it. And one of our big problems coming up in choosing how to implement a behavioral episode. So there's many different design options we have, and that we'll have to choose one side. It's going to be a difficult choice because we'll have to choose between the symbolic approach and the sub-symbolic approach, and then we'll have to wrap that in a ROS node somehow, and get them to communicate with other processes for working with them. Have I answered your question?
Yeah. Indeed, it's sometimes maybe frustrating when when we think about these things, we realize how difficult it is to because your first part of the answer was, well, you have to go down the full stack, right? You have to implement it. So it's a massive task. What if a student will like to start a master project or a PhD project on cognitive architecture? How will they do it?
Actually, I always advise students to beware of attempting to take on a cognitive architecture as a project, and because it's impossible. I mean, if you look at the timeline of these architectures, I mean, SOAR started in 1983. Most of them, I mean, the median length of time the cognitive architecture has been developed is 10 years. So you're not going to do it as part of a PhD and as a master's student. So my advice to you is find a good one and work with it, right? But don't. I only know of one PhD student who successfully developed his own cognitive architecture from scratch in a PhD, and that was in the Technical University of Munich, working with Gordon Cheng. That was our advisor, and it was a wonderful piece of work. Fantastic transaction paper out of it, but courage and kudos to him for sticking with it. It was tough. I think it's tough. So my advice would be find a good one like Isaac, like SOAR, like CRAM, like LIDA. They've gone open source. They've got I think a Python interface coming out now as well, and they're very open to share their work and work within that rather than trying to reinvent everything from the beginning with. I mean, it's a little like someone saying, I want to do research in operating systems. And, okay, so I'll build and design a whole new operating system so that I can do that. And that just is not a feasible way of approaching it. And it's not necessary either. You need to scope your contribution carefully. And it's difficult to do that, but not impossible. Yeah, I hope I've answered that question.
Yeah, very well. Since you're now on the slide with the Isaac architecture, I had again kind of a general question, but let's refer it to the Isaac architecture, which you mentioned is an hybrid architecture. I can clearly see some components of the cognitivist model in this architecture. If I have to look at the components of the emergent approach, where would you see them specifically?
Yeah, there are some symbolic representations in episodic memory. and also I think in the motivational system over here. The internal rehearsal system's purely symbolic. That was actually a graphics engine. So it's classified as hybrid, but with a little h, in the sense that I can't remember, there's some of the processes here are connectionist neural networks. I can't remember which ones. And so it's hybrid in this with this little h sense.
Yeah.
You know, and so when I talk about you know, it's going back up here to the only emergent one that actually takes this emergence seriously. So that by emergence, it means, we have to be careful with words. Emergence is a word which is misunderstood a lot, but effectively you get global behavior from the interaction of individual elements. And it would have been impossible to predict that behavior just by looking at the individual elements on their own. So there's a dynamic going on here. And that's what the emergent ones, and you can see there aren't that many of them. And they're not very mature, but because they focus on the self-organizational aspect of it. And
yeah, and what do you think is the case? Because I mean, of course, there is also as you explained well, like a tradition of the studies, right? So cognitivist approach is also the one that came first, and then maybe around the 80s, the emergent approach also showed some starting discussion, and then hybrid seems to be maybe now most promising because you basically take ideas from both worlds. But so, do you think definitely hybrid approaches are the way forward? And those emergent aspects that have been not maybe realized so much, is there potential, or you think there are like some basic fallacies there?
No, I don't think there are fallacies. I just think that the task of understanding the complexity of self-organizing systems is huge. And in fact, the emergent approach, actually, I think it predates the cognitivist one, because it actually goes back to the original cyberneticians. It goes back to all of the work that Wiener did, and Ross Ashby in particular, and what is it, Gray Walter? I always get that name wrong. But the point is that cybernetics approach, first order and second order cybernetics, is really got that emergent approach started, and it was then promoted, of course, so you're right, in the last 20 years with the rise of the embodied cognition approach and in action. And I personally am convinced that we need to be paying more attention to these self-organizing processes if we want to get the autonomy that we seek in our cognitive systems, and if we want to get the robustness and resilience and indeed flexibility. But the problem is scaling it so that it is capable of carrying out these complex tasks is not straightforward. And we kind of shortcut that with our rule-based approach, but it is a shortcut. It is a shortcutting. There's a very good argument on these videos that I showed you at the end, where it was in the panel discussion where somebody says, you know, cognition is not symbolic, and yet we have all of these symbolic approaches. But I personally think that the answer lies in the emergent area, and that's where. But it may not be my lifetime. In fact, it won't be in my lifetime. But I'm convinced it will happen, and I think we need to be paying a lot more attention to that, and make it hybrid, maybe with a bigger H, where you're investing self-organizing processes into your representational structures. That's where I think, and that's what I would like to spend most of my time doing.
Yeah, thanks for this comment. And I think this links to another question that I see now in the chat by Tom, when he says, he asks how important is biological plausibility, in your opinion, to implement this kind of large architectures. And for example, he's mentioning the unifying framework, mathematical frameworks such as the free energy principle, that they claim to be biologically plausible, and probably are to a certain extent. However, it might be difficult to scale to a large framework.
Yeah, but here I agree with you. I don't think you need to do this. I mean, we're doing cognitive modeling here. We're not doing brain modeling, right? So this is not the human brain project. So it's not working at that level of abstraction. It's,
right.
But that doesn't mean you can't use processes that we know which operate at a meta level in neuroscience. So, and exactly Friston's free energy principle is one of them, with active inference and predictive processing. So for those of you who don't know, this is the idea that effectively there's an organizational principle whereby you try and minimize the surprisal, or the you try and maximize the consistency of your internal models of how the world works with how the world works. So you minimize the surprisal. And you can model this formally two ways. You can model it by using neuronal networks, but you can also model it using information theory. And then this can provide you with your guiding organizational principle for how you would refine and enhance or cull your internal representations, your internal models, if you will. So it all will hinge on the concept of an internal model. And if you're not familiar with it, have a look at Daniel Wolpert's recent work on this, and his old work as well. The Hammer architecture was built on Daniel Wolpert's work. Wow, when was it? 1998. But one of his more recent papers really focuses beautifully on the importance of internal models in the different forms. And then the key idea, though, is that can we have an organizational principle like the free energy principle? And there are others. That's not the only one, which are biologically plausible, have their roots in really solid neuroscience, and then can be applied as computational theories to allow you to organize your representations and your behavior of your system at a meta level. And I think that that's exactly the type of work that we need more of, but there are people who are doing it. But of course, it doesn't, well, that's enough. Has that answered that question?
Yeah.
So I'm agreeing with the questioner. I think something like the inspiration of processes from neuroscience are going to be important, but you can apply them at a meta level. You don't have to. So somebody asked recently, should I be using spiking neural networks if I want biological plausibility? Yeah, but it's not clear that modeling it at the moment anyway. It's not clear that modeling your neural networks using spiking potentials is necessarily going to add anything to it. Just it is the way that nature does it, because it's very efficient. It's energy efficient, for example. But if you're not worried about that energy efficiency, you can still model your neural processes accurately without going to that level. Having said that, I would also point out that somebody said years ago that when we talk of neural networks today, we could equally call them potato networks, because a modern neural network, deep or otherwise, bears about as much resemblance to a biological neural network as a potato does. I mean, they are really, really simple abstractions. Real neurons work in a way more complicated way. So just bear that in mind. So.
Okay. Yeah, I think we took a lot of your time, David. Thanks so much for that.
It was a pleasure. I took a lot of your time.
And if you would like to just unshare your screen for a second, and we just say
escape. That's the question. Oh, I probably need to go back over to my.
Yeah, I think you have the square button on the top right.
So I was saying before we started, yet another platform.
There is a small square button on the top right. Oh yeah, that one. Okay. Yeah, to just say thank you, and I think it was very, very interesting, definitely for the students of cognitive robotics and for anybody else, the work PhD students and the work colleagues in the attending. and this we recorded and is gonna be available on YouTube. And yeah, very interesting discussion, and thank you very much for being with us.
Well, thank you again for the invitation, and I enjoyed being here, and I wish you all well, and we'll stay in touch.
Yes, thank you very much.
Bye-bye.
Bye-bye.